Hello viewers, this is Wagadaro now taking you through the story for A-level pure mathematics. And this video I'm going to go through the topic of partial fractions. So this video is suitable for students in both senior 5 and senior 6 offering principal mathematics as part of their combination. So before we start, I would like to share with you the course outline for pure mathematics, and this is the course outline. Pure mathematics is divided into 5 parts. One is algebra, then trigonometry. For algebra, you will expect 2 questions section A and 2 questions in section B. For trigonometry, 1 question section A, 1 question section B. For geometry, still 1 question section A, 1 question section B. Vectors, 1 in section A, 1 section B. And lastly, calculus, 3 in section A and 3 in section B. So what is ticked is what has been covered, and this video are going to go through the topic of partial fractions. So if a given fraction consists of a denominator which can be factorized, now this word can be factorized completely, it can be split up into component fractions, and these component fractions are what we call partial fractions. For example, if I have this and I want to add them up, I think you remember this from O-level, the first thing to do is to get the LCM. So LCM of this and this is this, the product. Therefore what I'm going to do, I'll say this LCM divided by this, x will cancel, you remain with x plus 1. Then x plus 1 times 2 gives you this part. What about for the other part? Remember there is a plus here, so you maintain the plus there. Then still you say this LCM divided by this, you realize that this and this cancels, you remain with x. So x times 3 gives you 3x, which is this part. Then when I open brackets for the numerator, I'll come up with this. Simply for like terms, I'll come up with this. Now this is a fraction whose denominator is factorizable. I think you see here it is factorizable. It has x as one factor and another factor as x plus 1. Therefore, if you split it, it means that you'll be able to get these 2 fractions. Now these 2 fractions are what we call partial fractions of this. So basically that is what partial fractions means. But in this case, moving from these partial fractions to this one fraction is easier because you simply get the LCM. But moving from this to get these component fractions is what this topic is about. So just start with splitting a proper fraction into partial fractions. So proper means that, proper in this case, it means that the degree of x in the numerator is greater than or equal to the degree of x in the denominator. So this one is proper because here the highest degree is 1, x power 1, but here if you expand you'll get x squared, therefore the degree is 2, meaning it is proper. But if this one, in the numerator it also had x squared, it implies that it will be improper. So we are going to start with the proper fraction. So proper fraction can be split into partial fractions provided its denominator factorizes. So partial fractions deals with denominator which is factorizable, and the factors of the denominator can be linear or quadratic or repeated factors, and the partial fractions for each case are got difference. So there are 3 cases of a fraction which can be split into partial fractions. One is where the denominator has factors which are linear. Then case 2 is where the denominator has factors which has a quadratic. Then 3 is where the denominator has factors which are repeated. So these are the 3 cases, and we are going to look at each one by one. So let's start with the first case where the denominator has only linear factors. Now linear means the highest degree is 1. If you see here, it is x plus a constant, so this is what we call linear. If it was quadratic, it means that here it would have been x squared. So if the denominator is a linear factor, or in the form ax plus b, the numerator will be a scalar. I think you see here that this denominator is linear, meaning that the numerator has to be a scalar. A scalar means a constant. For example, it can be 2, 3, 4, negative 1, negative a half, any. That is what we call a scalar. Or let's say an integer or a whole number or a fraction, as long as it doesn't have this variable x, we call it a scalar. So that means that you'll first let, because we don't know what is here, so we're going to first let it to be capital A for this factor, and also do the same for this factor, and put here another constant. So the constants must be different. If this is A, this will be B. It's not a matter that you use A and B. You can use K, K1, K2 like that, but it's easier to use A and B, A, B, C, D like that. So now this is how our partial fraction will look like, but we have to look for these values of A and B. Then also what we need to note is that we have put there an equivalent sign here. So this sign is not an equal sign. It is first an equivalent sign. We shall see why. Because when we put an equal sign, it becomes a formula, but here we want it to be an identity. So identity and the formula are different, and we shall see the difference as we proceed. So here A and B are constants and can be found, while A1, A2, A3 are known. So here they will not give you a constant. Here they will give you real values. It can be 3, 4, 5. That's what I said the constant means. But these ones, they don't give them to you, and it is you to look for them. But remember, we use an equivalent sign. So note that the LCM, or lowest common multiple, of a partial fraction on the left hand side is this, which is similar to the denominator of the given fraction. So this is what I mean. If you get the LCM of these two partial fractions, you'll be able to get this times this, which is the same as this. So in the end, you shall come up with this, because I think you remember how to combine this into one fraction. How you get the LCM, this LCM, divide by this, you realize this and this cancel, so you remain with this. So this times this gives you this part. Then after that, you maintain this plus sign, which is there. Then next is also this LCM divide by this, you realize this and this cancels, you remain with this, so this multiplied by this gives you this other part. Then from there, you'll remember here there's an equivalent sign. So what does it mean? It means that this one can cancel, so you remain with the numerators alone. So this numerator is here and this numerator is here. So our main step is this step, and remember there is an equivalent sign, not an equal sign. We shall see why. So this is an identity, and hence can be solved using any of the two methods. So if it was an equal sign, it ceases to become an identity, but if there's an equivalent sign, it is an identity. Now how do you get those constants A and B? There are two methods. One is by comparing coefficients, and for identities, if the right hand side is multiplied out, the coefficients of x squared, x, and the constant term will be identical on each side. So that is what an identity means. When you compare coefficients, they will be the same for each side. But for an equation, you have to solve. Then the second method is by substituting different values of x. So you look for suitable values of x and substitute in the identity. So you know that for an identity, left hand side is equal to right hand side for any value of x. So you just look for any suitable value of x and you substitute in both left hand side and right hand side, and you get an equation now which can be solved. Remember, an equation can be solved, but an identity cannot be solved. You just compare. But so when you substitute, it now becomes an equation, because now the equivalent sign, as we will see in the solutions, the equivalent sign will change and to become an equal sign. I think you realize that here we are using an equal sign. So that was the introduction. Now we shall go to questions. So we shall start with question 1, which came from UNEB 2008 paper 1 question 13a, and says use partial fractions to evaluate this integral. So like I said, always the denominator must be factorizable. So when I factorize this, I'll come up with this two factors, x minus 1, x plus 1. Then I'll split this one into partial fractions. I think you realize that these factors are linear, so meaning that the numerator will be a scalar or a constant. That is why here I'll come and put this one here, then here I'll put a value a. I don't know it, but I'll have to solve it. Then here I'll get this one here, then I'll put up a value b. I don't know it, I'll have to solve it. Then you realize that this is an equivalent sign. Then from there, I'll skip the step of getting LCM because my interest is the terms in the numerator. So numerator, this side it will be this. Then this side it will be this times this, which gives you that, and this times this, which gives you this. So if you want, you can go through that step of first getting LCM and combining these two fractions into one fraction, but there's no mark for that. Our interest is the numerators. Then also realize that I'm putting an equivalent sign here. So now we shall go to the steps of getting the constant. So remember we said there are two methods. One is comparing coefficients and another one is substituting suitable values. So in this question, I'm going to use the method of substituting suitable values. Now how do you know the values to substitute? You'll come here and say, if I want to make this one 0, the whole of this term 0, it means that this x minus 3 will be equal to 0. So when it is equal to 0, it implies that x is equal to 3. So what I'm going to do, I'll come and say that putting x equal to 3 in this identity, I'll come up with this. Because this one has become 0, then 3 plus 1 is 4. 4 times a is 4a. This one is maintained. Now, I think realize that after substituting, what comes out is an equation. It is no longer an identity. That is why here I'm putting an equivalent sign, but here I'm putting an equal sign. So after substituting, it must become an equation. And remember, equations are solved. So I'm going to solve this to come up with a equal to a quarter. The next is to also make this one, the whole of this term 0. To make it 0, I'll say that this is equal to 0, therefore x will be equal to negative 1. So I'll come here and write that putting x equal to negative 1, I'll come up with 1 this side, and here the whole of this is cancels because it becomes 0. Then this here, negative 1 minus 3 is negative 4 times b, you get negative 4b. When you solve this, you'll come up with b equal to negative a quarter. I think realize that now we put an equal sign because this step it was an identity, but this step it must be an equation. So now we have got a and b, therefore we can come and substitute for a here and for b here to get our partial fractions. So that is our partial fractions, but remember they told us to integrate. They told us to integrate this from 4 to 6. So I'll come and replace this one with this partial fraction. Therefore, I'll come and say that this integral which is required is the same as this integral. So what I've done, I've replaced this with this. A quarter is common, that is why it is pulled outside. So I think you remember how to integrate this. We have to put in natural logarithm. So integrate 1 over x minus 3 gives you ln x minus 3, and integrating this gives you ln x plus 1. This minus is maintained here. So this method of integration is under the topics of further integration. And that topic is available in this platform. So you just go to the playlist and look for the section of integration, then look for further integration. You realize you'll see video on integrating using natural logarithms, and that will be the video. So next is this minus this, it becomes a division. That is why you see here ln x minus 3 divided by x plus 1. A quarter is maintained. Now next is to substitute our limits. So substitute begin with the upper limit, then followed by the lower limit. You simplify, you come up with this. Then next is now to get the required value, which is that. So now we shall go to question 2, which came from UNEB 2006 paper 1 question 8, and says evaluate this correct to 2 decimal places. So if I think to realize is that the denominator is factorizable, so I'll factorize the denominator to come up with this, then split the whole of this into partial fractions to come up with this. The next is to, we are interested in the numerator, so the numerator for this side it will be 8x, then for this side it will be this times this, which is here, then this times this, which is here. So I think by now you know how to get that numerator. We use LCM, but that step of LCM can be skipped because it carries no mark. Our interest is the parts of the numerator. So next is to choose any of the methods. So the easiest one for this part, for this case, is the one for substituting suitable values. So to make this one 0, x will be equal to 6, so I'll come and substitute to come up with that, where a will be 6. Then to make this one is equal to 0, x will be equal to negative 2, so I'll come and substitute to come up with b as 2. Therefore my partial fraction will be this, where a is 6 and b is 2. I've got the partial fraction, but I've not yet integrated, so now let's integrate. So integrating this the same as integrating this, because we have seen they are the same. Therefore, we shall come and integrate. So integrating this gives you 6 ln x minus 6, and integrating this gives you 2 ln x plus 2. So like I told you, this method is under the topic of further integration. So next we substitute, begin with the upper limit, then followed by. So before you substitute, you can first bring this one here. Now why are we bringing that one here? Because you realize that if I just substitute this one here, I'm going to get 2 minus 6, which is negative 4, and ln of a negative is invalid. Therefore what we do, we have to first bring this one up, so that when we get a negative here, we power it by 6 to get a positive value. So when I do that, I'll come and substitute now for the upper limit first to come up with this, then lower limit to come up with that. Use the calculator and to 2 decimal places, and that will be the answer they wanted. So that was question 2. Now we shall go to question 3, which came from UNEB March 1998 paper 1 question 14b, and says evaluate this. So first of all, we said the denominator must be factorizable. So what I'm going to do, I'll first factorize this denominator. So extracting out this denominator alone, I'll come up with this. Then start by factorizing it. X first of all is common, so I'll first pull it out and remain with this in the bracket. Then I also factorize out that, because the sum, you look for 2 factors whose sum is positive 4 and product is positive 3. Those 2 factors are 1 and 3. That is why here this 4 has been replaced by 1 and 3. Then factorize out in this box bracket, you'll come up with this, because here for this 2 pull out x, you'll come up with this. For this 2 pull out 3, you'll come up with this. Then x plus 1 is common, so we'll pull it out and remain with x plus 3, which is here. So now that we have factorized it, we can now use our partial fractions. The next is to equate the numerators. This side it is this. Then for this side, you will say this multiplied by this and this, because that the LCM will be this times this times this. When divided by x, you will remain with x plus 3 and x plus 1. So that is why here you come up with this. Then for this one, you multiply by this, you multiply it with this and this to come up with this part. And for this one, you multiply it with this and this to come up with this part. Then next, I'll choose to start with 0, putting x equal to 0. That means that I'm going to make the whole of this 0 and the whole of this 0. So we'll come up with that. What if I put x equal to -1? Because it means that the whole of this is going to cancel and this is going to cancel, so remain with only this term and this term. So I'll come and get that as the value of c. Then when I put x equal to -3, it means that the whole of this is going to cancel and this one is going to cancel, so I'll remain with only b. So I'll come and get the value of b. So that is how they deal with identities. So now I've got the value of a, b, and c. I can now get my integral. So integrating 1 over x is ln x, but this third is there, so it remains there. This is 5 over 3, which is here. The integrating this gives you ln x plus 3. Then here there's nothing, so integrating this gives you ln x plus 1. Substitute the begin with the upper limit followed by the lower limit, you come up with that. Then lastly, this will be our answer. So they didn't specify the number of decimal places, you can use 4. So that was question 4. Question 3. Now we shall go to question 4, which came from UNEB 1997, paper 1, question 13, and says express this in partial fractions and hence evaluate that. Now the good thing here, they have tried to factorize, but the factorization is not complete because here there is difference of 2 squares. So what you're going to do, shall come here and factorize it further. This difference of 2 squares, it becomes 2x minus 1 and 2x plus 1. Then from there I'll split it into partial fractions to come up with that. Remember, note that we are using an equivalent sign here. The next is to get the numerator. Numerator for this side is this. Then for this other side, for this one, it will be this times this, which to give you this. Then for b, it will be multiplied by this and this to come up with this. And for c, it will be multiplied by this and this to come up with this. Now we shall start putting x equal to -3. Means that the whole of this is going to cancel, and also this will cancel, you remain with this, so we'll be able to get the value of c. Then putting x equal to 1/2, it means that this is going to cancel, so that is going to cancel, and also this is going to cancel, you remain with this part, so you can be able to get the value of a. What about putting x equal to -1/2? When I put x equal to -1/2, it implies that this is going to cancel and also this is going to cancel, so you'll be able to get the value of b. So now we've got the values of a, b, and c, therefore the partial fraction is that. Therefore, go to the hence part. The hence part, they wanted us to integrate with it when the limits are there. So I'll come and substitute this fx with these partial fractions. Then I'll integrate. Integrating, this gives you that, and this gives you this, and this gives you that. Hope by now you know how to integrate such. Then substitute limits and then use a calculator to come up with that value. So now we shall go to question 5, which came from UNEB 1994, paper 1, question 11b, and says find the area of the origin bounded by the curve this, the x-axis, and the lines x equal to 1, x equal to 2. So in other words, they want us to integrate this, but to integrate this, you realize that the denominator is factorizable, so I'm going to first split into partial fractions, then get the numerator and get the constants. Putting x equal to 0, I'll come up with a equal to 1. Putting x equal to 1, I'll come up with that equation, but I already know a, so I'll come and substitute to get the value of b. Therefore, this is equal to that. and now I can integrate because I know that area is equal to y dx, integral of y dx from 1 up to 2. So integrating this gives you this, and this gives you that. Then substitute limits, and then use a calculator. That will be the area they wanted. So that has been case 1, where the denominator has only linear factors. Now what if there is also a quadratic factor under the denominator? How do you deal with it? So if the denominator is a quadratic factor, i.e. in the form ax squared plus bx plus c, which cannot be factorized, because some quadratics can be factorized, but in case it cannot be factorized, then the numerator will be in the form ax plus b. In other words, the denominator will be linear. Remember, when the denominator is linear, the numerator is a scalar or is a constant. But in this case, when the denominator is a quadratic and that quadratic cannot be factorized, then the numerator has to be linear. That is why this quadratic cannot be factorized, so the numerator is linear. It will be ax plus b. For this one, the denominator is linear, so the numerator has to be a scalar. So that is what you need to remember. Then comparing the numerators, this one is here, and this one you'll say this times this to give you this part. Then for c, it will be c times this to give you this part. And the constants a, b, and c can now be obtained using any of the two methods, either by comparing coefficients or by substituting suitable values of x. So that knowledge, now let's go through these questions. Question 1 came from UNEB 2009, paper 1, question 10b, and says integrate this with respect to x. Now here, I think now you realize that the highest degree in the numerator is greater than the highest degree in the denominator. What does that mean? It implies that this is an improper fraction. But remember, the methods of partial fractions deal with proper fractions. So what does that mean? It means that you have to first do long division to get a proper fraction. Then it's that proper fraction where you will be able to use the methods of partial fractions. So what you're going to do, we are going to do some long division. So this one will be put here, then this one, what you want to divide, will be put here. So how is long division done? Long division for this one, you look at the highest degrees. Here the highest degree is x power 4, and here the highest degree is x power 3. So what you're going to do, you'll say x power 4 divided by x power 3. What do you get? Same base, subtract the powers, you'll be able to get x. So you come and put x there. After that, you'll come and say this x multiplied throughout by the whole of this divisor, you'll be able to come up with this. Now after that step, we are going to do some subtraction. So we are going to subtract this from this. So this minus this gives you 0. This minus, here there is nothing like x cubed, so negative x cubed minus 0 is negative x cubed. Then this minus this cancels. Then 1 minus 0 gives you 1. Then you still do the same. Highest degree is this, and here highest degree is this. So this divided by this, you come up with negative 1. Then negative 1 multiplied by the whole of this divisor, you'll come up with that. After that, we are going to do some subtraction. When I subtract, I'll come up with that, because this cancels. Then here 0 minus x gives you positive x. Then 1 minus 0 gives you positive 1. So in that case, now this one is what we call the divisor, and this is what we call the remainder, and this is what we call the quotient. So what we are going to do, this improper fraction will not be proper by saying this quotient is here plus this remainder, which is here, divided by the divisor, which is that. Now in this case, this one is okay, but this one is now a proper fraction. So the methods of partial fractions will only deal with this proper fraction. So proper fraction, this one can be factorized to come up with this. So here this one is linear, that is why here up with the numerator is a scalar. But for this term, this is a quadratic and it cannot be factorized, so the numerator must be linear. After that, you'll equate the numerator. So here the numerator is this, and this side the numerator will be got by saying a multiplied by this gives you this, and this multiplied by this gives you that. Okay, so now we have been using the method of substituting suitable values of x. So in this case, let us try the second method where we have to compare coefficients. Now, when I compare coefficients of x power 0, means that it's a constant. So x power 0, here there is this one, and this side there will be this and this, only that. So come and say that a1 is equal to a. Now we have got the value of a. What about comparing coefficients of x power 1? Here there is 1 here. What about here? This side there will be c. So we'll come and say that 1 is equal to c. What about comparing coefficients of x power 2? X power 2, this side it is 0 because there is no x squared, but this side there is this a, and there is also this b, because x times x gives you x squared. So I'll come here and say that 0 is equal to a plus b. The good thing, I already know the value of a, so I'll come and substitute to be able to get the value of b. So now I've got a, b, and c. Therefore I can come and write my partial fraction and then integrate. So that is my partial fraction, and now when I integrate, I'll come up with that integral. So what I've done here, I think realize that this one has been split further for easy integration. Now how has it been split? This LCM will be common, so this numerator will say negative x over this to give you this. Now the negative is because of that is catered for by this minus, then plus 1 over this to give you that. So that is called splitting the numerator, and it simplifies the process of integration. Then from there I'll come and integrate x. I'll come up with a half x squared. Integrate 1, I'll come up with x. Integrate 1 over x, I'll come up with ln x. Integrate this, I'll come up with a half ln 1 plus x squared. Integrate this, I'll come up with arctan x. I think remember this. So for you to know how to integrate this, you'll go to the part of tan substitution, integration by tan substitution. It's also available, the video is available in this platform. So just go under further integration and look for integration by tan substitution. You'll be able to learn how to integrate this to come up with this. Then because it is an indefinite integral, you have to add the constant of integration. So now we shall go to question 2. Question 2 came from UNEB 1999, paper 1, question 14, Roman 1, and says find this integral. So the denominator can be factorized because there is difference of two squares. So difference of two squares, this gives you that, but this one also there is difference of two squares, so you still factorize it further to come up with that. Then now you can use partial fractions. Here the denominator is linear, so the numerator is constant. Denominator is linear, numerator will be a scalar. Denominator is quadratic, so the numerator must be linear. The next is to extract out the numerator. So numerator this side, it will be this. Then this side, it will be this a will be multiplied by this and this to come up with this part. Then the b will be multiplied by this and this to come up with this part. And this cx plus d will be multiplied by this and this to come up with this part. Then now it is up to you to choose any of the two methods, either to compare coefficients or to choose a suitable values of x. So let me choose the method of choosing suitable values of x. So when I want to make the whole, when I put x equal to 1, the whole of this is going to cancel. Sorry, this will not cancel. It is this one which is going to cancel because it will be 1 minus 1. And also this will cancel, so I can be able to get the value of a as a quarter. So now I'll come and put x equal to -1. So when I put x equal to -1, this one is going to cancel because it will be -1 plus 1, and it will cancel. Also this one will cancel because it will be 1 minus 1, which is 0. So I can be able to get the value of b. So I'll come and say that my value of b will now be -1/4. What about when I put x equal to 0? When I put x equal to 0, this is what is going to happen. When I put x equal to 0, this will remain, but this one is going to cancel. This c will cancel. So I'll get an equation having a, b, and d. So let's do that. So that is what I'm going to get. The good thing, I know a and b, so I can be able to get the value of d. Then when I put x equal to 2, I'll get an equation having all the terms a, b, and c, and d. So the good thing, I know a, b, and d, so I can be able to get the value of c, and c will be equal to 0. So now I've got a, b, c, and d, so I can come and write my partial fraction. So that is the partial fraction, but remember they told us to integrate, so I'll come here and integrate that partial fraction. So this integral is the same as that integral. So I'll come and say that integrating this gives you a quarterly in that, this gives you a quarterly in that, this gives you a half arctan x plus c, which is the constant of integration. Then I can choose to simplify because the quotient is common, so I can say this is a quarter, then this minus this gives you a division. But even if you stop here, you'll still get all the marks. So now I shall go to question 3, which came from UNEB 1995, paper 1, question 10a, and says, express this as partial fractions and hence otherwise find this integral. So the good thing here, the denominator has been factorized for us. But what we need to realize is that the degree here is x cubed and also the numerator is x cubed. What does that mean? It means that it is an improper fraction. Remember, in this case, an improper fraction is when the degree of the numerator is either equal to the highest degree on the denominator or greater than the highest degree in the denominator. So in this case, the degrees are the same. The highest degree in the numerator is x cubed, and also in the denominator is x cubed, so it still remains an improper fraction. So what do we do? The first thing to do is to do long division. So long division, it will be that I'll first expand this to come up with this, then I'll bring this divisor here and this one here, the one to be divided. Then I'm going to start my division. Remember, the process is the same. You look at the highest degree here and the highest degree here. So this divided by this gives you 1, so I shall put 1 there. Then this one will multiply throughout the whole of this divisor. So that will give you that. The next is to do some subtraction. So when I subtract, this cancels and I'll come up with this. Because now here I think realize that 0 minus this gives you positive that. Then 0 minus this gives you negative that. And negative 3 minus negative 2 gives you negative 1. Now when you look at this one, the highest degree is 2 and the highest degree here is 3. So you cannot divide them. So you stop there and you come and conclude that this one is equal to 1 plus this over this. So now we can now do our partial fraction, because now this one is now a proper fraction. So here the denominator is linear, numerator has to be a scalar, denominator is quadratic, numerator has to be a linear. So extract out the numerators. So this side should be this, for this side should be this, a multiplied by this to give you this, then this one multiplied by this to give you that. Then you can choose any of the two methods. Let me choose the one of substituting suitable values. So when I substitute x equal to 2, it implies that the whole of this is going to cancel and I'll be able to get the value of a. When I substitute x equal to 0, it implies that both will remain. This is going to remain and this is going to remain, but this one is going to cancel. So I can be able to get the value of c, because when I substitute for a, I'll get my c as that. The next is putting x equal to 1. When I put x equal to 1, this is going to remain. All of them are going to remain. So I'll come and substitute. I'll get an equation with having all a, b, and c. Then I'll come and substitute for a and for c to come up with the value of b as that. So now I've got a, b, and c. Therefore, I can rewrite my partial fraction as that. Therefore, the hence part we are going to integrate. So when I integrate, I'll come up with this integral being equal to this. Therefore, integrate 1 gives you x, integrate this gives you ln that, integrate this gives you half ln that, and integrating this gives you arctan x plus a constant of integration. So now we shall go to question 4, which came from UNEB 1992, paper 1, question 11b, and says, given this is equivalent to this, determine the values of a, b, c, and d, and hence evaluate this integral. Now the good thing they have speech for us how the partial fraction will look like. So what we need is to extract out the numerator and then use any of the two methods to get the constants. So when I sort out the numerator, this left hand side to be this and this side to be a will be multiplied by this and this to come up with this. Then b will be multiplied by this and this to come up with this, and cx plus d will be multiplied by this and this to come up with that. Now next is to choose any of the two methods. Let me choose the one of substituting suitable values of x. So when I substitute x equal to 1, this is going to cancel, and also this is going to cancel because it will be 1 plus 1, which is 2, minus 2, which is 0. So I can be able to get the value of b. Then when I substitute x equal to negative 2, I'll be able to get the value of a. When I put x equal to 0, I'll be able to get that equation, but I already know a and b, therefore the value of d can be got. And when I put x equal to 2, I'll be able to get that equation having a, b, c, and d. The good thing, I know a, b, and d, therefore I can simplify to get the value of c. Therefore a, b, and c, those are the values of a, b, c, and d. But they told us that hence evaluate this. So we shall come here and do our integral. So for the hence part, this integral is the same as this integral. Therefore, I'll come and integrate this to give you this, this will give you that, and this will give you this. Substitute limits to give you that, and then use a calculator to come up with that. So that was question 4. Now we shall go to question 5, which came from UNEB 1990, paper 1, question 11b, and say that show that this is equal to that. So the good thing, they have already factorized for us the denominator, so we are going to just substitute. Remember, this is quadratic, so the numerator has to be linear. This is also quadratic, the numerator has to also be linear. Then extract out the numerator. This side should be this, and this side, this will be multiplied by this to give you this, and this will be multiplied by this to give you that. Then choose any of the two methods. Let me choose the one of comparing coefficients. So comparing coefficients, I'll start with x power 0. This side there is 6, and this side there will be this and this, which is 9b, and also this and this, which is 4d. And that is equation 1. What about coefficients of x power 1? Here there is 0, that's why you see 0 there. Then this side there is this by this, which gives you this 9a, and there is also this by this, which gives you this 4c. What about coefficients of x squared? So here there is this, which is 1 here. Then here there is this by this, which gives this b, and here there is this by this, which is this d. Then coefficients of x cubed. X cubed, here there is 0, that's why you see this 0 here. Then here there is this by this, which is this, and also this by this, which is that. Now next is, these are 4 equations and 4 unknowns. You have to solve them simultaneously. So I'll begin by equation 1 minus 4 times equation 3. So I'm applying 4 throughout here to come up with 4b, then here to be 4d, and here to be 4. Therefore when I subtract, it will be 9b minus 4b, which is 5b, then 4d minus 4d, which is 0, 6 minus 4, which is 2. Therefore b will be 2 over 5. Now from equation 3, I've got b, now I can be able to get the value of d, and d will be 3 over 5. Then equation 2 minus 4 times equation 4, so this is equation 2, and this is equation 4, so 4 by this gives you 4 here, and 4 here, and here to remain 0. So this minus this gives you 5a, and then 4c minus 4c gives you 0. Therefore a will be 0. Then from equation 4, I already know a, I can be able to get the value of c, and c will also be 0. So I've got the values of a, b, c, and d. So I'll come and substitute, get my partial fraction. But they told us to get also the integral. So integrating this is the same as integrating that. Then I'll come here and say that this integral is the same as this, and this is the same as that. So substituting limits, start with the upper limit followed by the lower limit to come up with this. Upper limit followed by the lower limit to come up with that. Now here we can't use the calculator because they told us to prove. I think you remember, if you look at this question, they told us that to prove that's equal to pi over 20, so we cannot use the calculator. We have to simplify until we get pi over 20. Now how do we simplify? This 1 over 5 is common, so we have this. Now we have to deal with this until we get pi over 20. So how do we do that? We are going to let. So let alpha be equal to arctan a half, therefore tan alpha is a half. Also let beta be equal to arctan a third, therefore tan beta will be equal to a third. Therefore we already know that tan alpha plus beta is the same expanded as tan alpha plus tan beta over 1 minus tan alpha tan beta. Then come and substitute. We know that tan alpha is a half and tan beta is a third. Then divide by 1, which is here. Tan alpha is here, multiply by tan beta, which is there. Use the calculator, you'll come up with 1. What does that mean? It means that alpha plus beta is equal to arctan 1, which is pi over 4. Then I think you recall that from the integral, we had got 1 over 5 in brackets arctan a half plus arctan a third. But this one is alpha and this one is beta. I know that alpha plus beta is equal to pi over 4. Therefore the whole of this multiplication gives you pi over 20, which is required. So now shall go to question 6, which came from UNEB 1989, paper 1, question 6b, and says evaluate this. So from geometry, from algebra, this one can be factorized to give you this. Then from there we shall now use partial fractions. So denominator is linear, numerator is scalar, denominator is quadratic, numerator is linear. Then you extract out the numerators. I think you know how, by now you know how. Then you are going to put x equal to 1 to come up with that. Therefore a will be equal to 2. Then put also x equal to 0, come up with that. You already know a, so you'll be able to get c. Then put x equal to -1, you come up with that. Therefore you already know a and c, so you can get the value of b. So now I've got a, b and c. I can now go and get the partial fraction and integrate it. So integral of this is the same as integral of that. So I come and integrate to come up with that. So this gives you this, and this gives you that. Substitute limits. When I substitute limits, I'll come up with that, and that will be the answer. So that has been case 2, where the denominator has a quadratic. Now what if the denominator has a repeated factor? How do you deal with that? So there we also expand in a certain way. For example, if this is the repeated factor, I think you say that power n, how do you do it? You keep on go on writing that factor but increasing the power. So start with this factor to power 1, go to that factor power 2, power 3, and continue until you reach this value of n. So if here it was squared, it means that you would have stopped here. If this was 3, it would have stopped here. If it is 4, you'd have gone the second part, another part which has power 4, like that. So increase from 1 up to that given power. So that is how we deal with repeated factors. You don't expand this one, you just keep on increasing from 1 up to that factor. Here putting there a scalar. Now I think you realize that here, if you expand this one, you'll be able to get a quadratic, but here we put a scalar because this was got from a repeated factor. So basically that's the only difference, the rest is the same. So let's see questions in that form. So question 1 came from UNEB 2015, paper 1, question 13, and says that express this as partial fractions and hence evaluate this correct to 3 decimal places. Now this one has a repeated factor because we see here x squared. So first start with power 1, then go to power 2, like that. Now because the power is 2, we have to stop at 2. But we also have another factor which is x minus 1, so we'll come and put it there. Therefore next is to extract out the numerators, then choose any of the two methods. Let me choose the one of substituting suitable values. So when I put x equal to 0, I'll get b as -1. Put x equal to 1, I'll get c as 1. Put x equal to -1, I'll come up with that, but the good thing I know b and c, so I can get the value of a. Therefore the partial fraction is that. So we have done this part of expressing as partial fraction. Now we have to go and integrate. So for the hence part, integrating this is the same as integrating this. Therefore this gives you ln that, and this gives you ln that, and this gives you 1 over x. Negative, now this gives, integrating 1 over x squared is negative 1 over x, but the negative is this negative minus, and the negative in the answer gives you a positive value there. Then substitute limits begin with the upper limit followed by the lower limit, and then you can use your calculator to get the value to the required number of decimal places. So that was question 1. Now we shall go to question 2, which came from UNEB 2013, paper 1, question 15. Says resolve this into partial fractions and hence find this integral and dy dx. So the good thing, they already factorized for us the denominator. So come and say, remember here there is a repeated factor. So you begin with power 1, go to power 2, and stop there because this stops at power 2. But there's also this other factor which is here, but this factor is quadratic, so the numerator will be linear. So next is to extract out the numerators and then start using any of the two methods. Let me choose the one of using suitable values of x. So putting x equal to 1, I'll come up with b as 2. Putting x equal to 0, I'll come up with that. And the good thing, I already know b, so I'll come and substitute for b and get that expression. Then putting x equal to 1, negative 1, I'll come up with that. Then come and substitute for b and also for d to come up with that. So I now have that equation having c and a. Then putting x equal to 2, I'll come up with that. Then come and substitute for b, c and d to come up with that. So a is equal to 1. Now that I've got a, I can be able to get the value of c and also the value of d. Then I'll come and write my partial fraction. It will be in that form. Now for the hence part, we have to also integrate and also differentiate. So integrating this gives you is same as that. So you need to recall something, that this integral is somewhat similar to this one, and to be equal to 1 over ab arctan that. So when you remember that, we shall come up with this value. So this one is easier, it is ln that. This one is also easier, it is negative that. But this one, first pull out this 4, then remain with 1 over x squared plus 2. So that means that if you compare, a squared is 2, meaning that a is root 2. That is why you see here to here, root 2 here. B is already 1. If you look at this, that is why here you see 1 over root 2. Then inside arctan there is bx over a. Now b is 1, but a is root 2. That is why you see here x over root 2. So that is how they integrate such integral. So this method is still under further integration in the video of tan substitution. So I can come and simplify to come up with this as the required integral. So now shall go to dy dx. So dy dx, first of all, why is that in partial fractions? When you use negative indices, you shall come up with that. The next is to now differentiate. So when I differentiate, I'll use the same knowledge, bring down the power to come up with negative 1 here, reduce the power by 1, so negative 1 minus 1 gives you negative 2, then multiply by the derivative of the inner bracket, so differentiating this gives you positive 1. Then here, bring down the power, negative 2 times 2 gives you negative 4, then reduce this power by 1 gives you negative 3, derivative of the inner bracket is positive 1, which is there. Then you bring down the power, negative 1 times 4 gives you negative 4, reduce the power by 1 gives you negative 2, derivative of the inner bracket gives you 2x. So I can simplify to come up with that as dy dx. So that was question 2. Now shall go to question 3, which came from UNEB 2005, about 1, question 15. Says, express this into partial fractions. Hence, evaluate this and give your answer to correct to 3 decimal places. So still, we shall first express into partial fractions. This is now cubed, so we'll begin with power 1, go to power 2, and lastly power 3. Then extract out the numerators. Then use any of the two methods. If I use the one of suitable values, I'll first put x equal to 2 to come up with that. Then when I put x equal to negative 1, I'll come up with d as that. Put x equal to 0, I'll come up with that. Then substitute and get an equation having b and c, which is that. Then put x equal to 1, I'll come up with that. Substitute and simplify until you come up with the value of c. After getting c, I can be able to get the value of b from here. So now I can write my partial fraction, which will be that. Then for the hence part, I have to integrate. So integrating this gives you this. Then integrating this gives you this gives you this, and this gives you that. The next is substitute limits. Upper limit minus lower limit, then simplify. But remember, they want the answer to 3 decimal places, so that will be the answer. So now we shall go to question 4, which came from UNEB 2004, paper 1, question 12, and says, express this into partial fractions and hence evaluate this correct to 4 decimal places. So this one will be equal to this. So the power is 2, so you begin with power 1, go to power 2, and stop there. Then extract out the numerators. Then use any of the two methods. When I choose the one of substituting suitable values of x, I'll begin by putting x equal to -1 to come up with that. Therefore, b is a half. Then we also put x equal to 5 to come up with that. Therefore, c is 7/12. Put x equal to 0, come up with that. Substitute, and be able to get the value of a as that. So I've got a, b, and c. I can now come and get my partial fraction, which is that. And for the hence part, I'll have to integrate. So integrating this gives you this, and this gives you this, and this gives you that. The next substitute limits. Begin with the upper limit followed by the lower limit. But they want the answer to 4 decimal places, so it will be that. Now we shall go to question 5, which came from UNEB 2000, paper 1, question 14, and says, express this into partial fractions and let's evaluate that. So this is quite solved, but first begin with power 1, then go to power 2 and stop there. Then extract out the numerators. So I think you realize that the procedures are always the same. Then choose any of the two methods. When I put x equal to 2, I'll come up with that, therefore a is a third. Put x equal to -4, come up with that, therefore c is 4. Put x equal to 0, I'll come up with that. Substitute for a and c, I'll be able to come up with the value of b as -a third. So I've got the values of a, b, and c, therefore the partial fraction is that. But they also want us to integrate, so I'll come and integrate. So integrating this gives you this, and this gives you this, and this gives you that. So I can choose to simplify further. I can either stop here or I simplify further, and it is okay. So now we shall go to question 6, which came from UNEB 1991, paper 1, question 13b, and says, evaluate this, and it has 8 marks. So still we shall first express in two partial fractions. This is power 2, so I'll first begin with power 1, followed by power 2, and stop there. Then extract out the numerators. And choose any of the two methods. So when I put x equal to 1, I'll come up with that, therefore c is that. Put x equal to -2, I'll come up with that, therefore a is that. Put x equal to 0, I'll come up with that. Substitute for a and c, I'll come up with the value of b as that. So I've got a, b, and c, therefore the partial fraction is that. But remember, they want us to integrate, so I'll come and integrate. So this integrating this gives you this gives you that, and this gives you this. Then substitute limits, upper limit first, followed by the lower limit. Then use a calculator to come up with that value. So by now I believe you have mastered the concept of splitting a proper fraction into its partial fractions. So now you're going to go to splitting the numerator for quotient polynomials. So this method is used for fractional integrands whose quadratic denominator can't be written in simple partial fractions. So there are various cases. So the first case is the method of dividing each term in the numerator with the denominator. And question 1 says find the integral of this with respect to x. So that means that each term in the numerator will be divided by the denominator. Therefore, this will be 1 over x squared plus 1 plus. So this plus here is what is here. Then x over x squared plus 1. With that, I can now easily integrate, because this one is the standard integral. It will be arctan x, and this one to be a half ln x squared plus 1. So all these methods are available in the video of further integration, and that video is also available on this platform. So now we shall go to question 2, where they want us to find this integral. So still we shall use the method of splitting the numerator. So each term in the numerator will be divided by the denominator. So this will be 2x over 4x squared plus 3. Then this minus is maintained here. Then this one to be 1 over 4x squared plus 3. The next is integrating this gives you, without this 2, so this 2 is first maintained. Then integrating x over 4x squared plus 3 gives you 1 over 8 ln 4x squared plus 3. So those methods are available under the top video of further integration. The integrating this gives you 1 over 2 root 3 arctan of 2x over root 3. So this is also a standard integral. So in the end, we shall come up with that as our answer. So now we shall go to case 2, which involves splitting the numerator into 2 parts, one of which is a multiple of the derivative of the denominator. Therefore, in this case, the fractional integrand will be expressed as 2 fractions which are easily integrated by using the formula that the numerator will be equal to a plus derivative of the denominator plus b, where a and b are constants. For example, if they tell you to find such an integral, the first thing to do is to get the derivative of the denominator. So this derivative of this will be 2x plus 4. The next is to recall this formula. The numerator will be equal to a multiplied by the derivative of the denominator plus b. So this step can be written, or you can skip it as long as you remember this. So you shall come here and put that the numerator is equivalent. So yeah, it was supposed to be equivalent to a plus a multiplied by the derivative plus b. Then from there, we use the methods for identities, either the 2 methods we have been looking at. Either you choose suitable values of x, or you compare coefficients. So I'll choose the one of choosing suitable values of x. Therefore, when I put x equal to 0, I'll come up with b equal to 3 minus 4a. When I put x equal to negative 1, I'll come up with b equal to 1 minus 2a. Therefore, when I equate the 2 equations, because they are both equal to b, I'll come up with 3 minus 4a equal to 1 minus 2a. Then make a the subject, a will be equal to 1. Then from here, I'll realize that b is also equal to negative 1. Therefore, this given integral is the same as this plus this. So this is a, remember a is 1. So a times the derivative gives you that minus, because of this negative 1. So minus dx over this denominator. But you already know that this one can be, you can complete squares, so this becomes this. So how does it come about? You look at first these 2 terms. These 2 terms, you'll come and say that x plus half of this coefficient of x. So half of this coefficient is 4 over 2, which is 2. That is why you see 2 here. Then in brackets you square it. Then minus the square of this term, which is 4. Then after that, we shall remember that there was also plus 7 here, so we bring it back here. So that is what we call completing squares. So that is on algebra. So negative 4 plus 7 gives you positive 3, which is that. So what we have done, we have completed squares. And why do we complete squares? It is because this denominator cannot be factorized completely. Therefore, come and say that this one now, it was this, so I've replaced it with that, the one we have completed squares. Then from there, I will recall that dx of a squared, dx over x squared plus b squared x squared is equal to 1 over ab arctan bx over a plus c. That is, this proof was also seen under the video of further integration. So I'm going to use it. If I use it, it implies that when I compare this b, this 3 is the same as a squared, meaning that a is equal to root 3. Then the b squared will be 1, because the coefficient here is 1. Then where there is x, I'll put there x plus 2. So when I do that, this is what I'm going to come up with. 1 over ab is the same as 1 over root 3 times 1, which is 1 over root 3, which is here. Then bx over a, b is 1, then x we have been replaced with x plus 2, that is why you see here x plus 2, then over a, and we saw that a is root 3, that is why it is here. So now we shall go to question 2. Question 2, they want to find this integral. So still do the same. First differentiate the denominator to come up with this. Then that means that the numerator is equivalent to a multiplied by the derivative plus b. Then choose any of the two methods. So when I put x equal to 0, I'll come up with b equal to 7 minus 5a. When I put x equal to negative 1, I'll come up with b equal to 4 minus 3a. When I equate the two equations, I'll come up with 4 minus 3a equal to 7 minus 5a. Make a the subject, a will be 3 over 2. That means that b is equal to negative a half. Therefore, the partial fraction is that. Now, next is to integrate. So when I integrate this, I'll come up with this. I integrate this. So this one, I cannot integrate it easily. The first thing to do is to complete squares. So when I complete squares, I'll come up with this. So now that I've completed squares, I can go ahead and use the method for after completing squares, then that is tan substitution, which you have already seen that dx over a squared plus b squared x squared is equal to that. That when I use that and compare, I realize that this integral is equal to that. So this division here can become a multiplication by changing the reciprocal. In the end, I'll come up with this as the integral for this. But that, remember, that is not the end. We have to come and conclude that therefore this integral is equal to this minus that plus the constant of integration. That was question 2. Now shall go to question 3. Find this integral. So still we shall do the same. Differentiate this inside the square root. When I differentiate, I come up with negative 2x minus 4. Therefore, come and write that this one is equivalent to this. But this is my main interest, equating the numerators. So, putting x equal to 0, I'll come up with that equation. Putting x equal to a half, so here there is an x. I'll come up with that equation 2. So I have two equations, two unknowns. I have to solve them. Subtracting 1 minus 2, I'll come up with a equal to 1. Therefore, from equation 2, I'll be able to get the value of b as 5. That means that this one is the same as, or is equivalent to that. Therefore, this given integral is the same as integrating this and that. So here we have to recall this. So this one will help us to integrate this. This one is easier because you increase the power by 1, divide by the new power, since this is function and its derivative. I think you remember that method, and which we had already covered it previously. So using this for this, you realize that a squared is 9, meaning that a is 3, then b squared is 1. And where there is x, we shall put there now x plus 2. So when we do that, we are going to come up with this. So for this first term, it's easier. You increase the power by 1 and divide by the new power. Then for this one, you use that comparison, we shall come up with 5 arcsine of x plus 3 over 3 plus c. Simplify, you'll come up with that. So you can either choose to stop at this point or you complete this. That was question 3. Now we shall go to question 4, which is that find this integral. So still we shall do the same, get the derivative of what is inside this bracket. It will be 2 minus 2x. Therefore this is the same as this, but our interest is equating the numerators, which is this step. Therefore, putting x equal to 1, I'll come up with b as negative 3. Putting x equal to 0, I'll come up with that equation. The good thing, I know the value of b, therefore the value of a will be 2. Therefore, this given fraction is the same as this. Now this one is easier to integrate, but this one is not easier to integrate, so the first thing to do is to complete squares for the denominator. So when I complete squares, I'll come up with that. Therefore, I'll come and say that my integral is the same as this minus that. So the first one is easier because we increase the power by 1, divide by the new power, but this one we have to use this expression of sign substitution, which you already saw under further integration. So for this one, increase the power by 1, divide by the new power. So this 2 is what is here, we just maintained it. Then when it comes here, you have to compare, meaning that a squared is 2, meaning that a is root 2. Then x minus 1 is the, we replace x, and b squared is 1. So when we use that, we shall come up with this as our integral. Therefore, I can choose to stop here, or I can complete like that. So now shall go to splitting the numerator for quotient trigonometric functions. So we have been dealing with quotient polynomials. Now shall go to quotient trigonometric functions. The difference is that now the numerator is equivalent to a multiplied by the derivative of the denominator plus b multiplied by the denominator. Previously, for polynomials, this multiplication is not there, but when it comes to trig functions, we have to include it there. So always remember that. So I'll use that to go through some questions. So question 1 says find this integral. First thing to do is to get the derivative. So the derivative of that is this. Next is to, you can either choose to skip this step or to write it, but our interest is the step of equating the numerator, which is here. So this is the step of interest, whereby this is the derivative and this is the denominator. Then now you can choose any of the two methods. So if you choose the one of substituting, now what you need to remember is that now here, since they are trig functions, the calculator has to be in radians. I think you remember that under integration of trig functions. So substituting pi over 2, x equal to pi over 2 shall come up with that, implying that b is equal to negative 2a. Then substituting x equal to 0, I'll come up with that, when I implying that 1 is equal to negative a plus 2b. Therefore, when I substitute, I already know that b is equal to negative 2a. So where there is b, I'll put the negative 2a to give me that. To get only a as the only unknown, therefore a is equal to negative 1 over 5. And b is equal to 2 over 5. After getting a and b, I can now integrate what I want. So this one is the same as this integral. Therefore, I'll just come and say that the answer will be this, will be that, and this will be that. Why? Because you think you realize that this one, okay, so for this one, I think you see that the numerator is the derivative of the denominator, therefore that is why there is ln. But for this one, the whole of this cancels with this, so integrating 2 over 5 gives you 2 over 5x. So I believe now you realize why we made the numerator to be in the form a multiplied by the derivative of the denominator plus b multiplied by the denominator. So you can either choose to stop here or you conclude in this way. All is okay. That was question 1. Now we shall go to question 2, where they want you to integrate this. So still we shall do the same. First differentiate the denominator to come up with this, then get the numerator, express the numerator in terms of a multiplied by the derivative of the denominator plus b multiplied by the denominator. So this is our main line we want. Then we shall use any of the two methods. So when I put x equal to pi over 2, I'll come up with that, implying that b is equal to 3a minus 2 over 4. When I put x equal to 0, I'll come up with that, therefore implying that b is equal to 1 minus 4a over 3. Now equating the two equations, I'll be able to get the value of a. So simplifying gives you that value of a as 2 over 5. And the value of b will be equal to 3a minus 2 over 4. The good thing, I know the value of a, therefore I'll come up with negative 1 over 5. Therefore, this integral is the same as this integral, therefore, which gives me this. So this gives me this because the numerator is the derivative of the denominator. For this one, the whole of this cancels with this. So integrating 1 over 5 gives me 1 over 5x. That was question 2. Now I shall go to question 3, where I want you to find this integral. So still the procedure is the same. First differentiate the denominator, then express the numerator in terms of a plus derivative of the denominator plus b multiplied by the denominator. So this is the line of interest. Next is to substitute. So when I put x equal to pi over 2, I'll come up with that, b as that. Then when I put x equal to 0, I'll come up with that, which gives me that equation. So next is to equate the two equations. So when I equate the two equations, I can easily be able to come up with the value of a. Therefore, the value of a will be negative 27 over 106. And the value of b will be 91 over 106. Therefore, this integral is the same as this plus this. And still the same procedure. This is natural log, and this one you just add x because this and this cancels. You can either choose to stop here or you can rearrange. So now shall go to integration by first changing the variable and then using partial fractions. So question 1 says integrate this. The first thing to do is to let the denominator to be equal to a variable, let's say u. So u will be equal to ex minus 1. When I differentiate u with respect to x, I'll come up with du dx being equal to ex. When I make dx the subject, by taking this side and this side, I'll come up with dx being equal to du over ex. But the good thing, I know that u is equal to ex minus 1. Therefore, when this one goes this side, I'll come up with ex equal to u plus 1. That is why you see here u plus 1. Therefore, I come and substitute the whole of this was u, which is here. Then this dx was this, so I'll come and substitute it there. So in the end, I'll come up with 1 over u in brackets u plus 1 du. And this one, you realize that the denominator is factorizable, meaning that the next option, the option is to use partial fractions. Therefore, this will be equivalent to this, and therefore, one equating the numerators, 1 is equivalent to a in brackets u plus 1 plus bu. So putting u equal to 0, a will be equal to 1. Putting u equal to negative 1, b will be equal to negative 1. Therefore, this integral is the same as this integral, so I'll have to integrate it. Integrating 1 over u gives me ln u, and integrating 1 over u plus 1 gives me ln u plus 1 plus c. But remember, we are the ones who introduced in the u, so we have to again replace u with ex minus 1, and u plus 1 was ex. Now here ln e cancels to remain with only x, which is here, because ln e is equal to 1. Now I shall go to question 2, saying that using the substitution u squared equal to x cubed plus 1, show that this is equal to that. So we know that u squared is equal to x cubed plus 1, meaning that x cubed is equal to u squared minus 1. So differentiating this, both sides with respect to x, this differentiating u squared will give me 2u du dx, and differentiating this will give me 3x squared. Making dx the subject gives me 2u over x over 3x squared du. So because we have changed the variable, we also have to change the limits. So the ones of x are 1 and 2. And what about the ones of u? The ones of u, we shall come here and put the value of u x here to be able to get the value of u. So when I put 1 here, it will be 1 cubed is 1 plus 1 is 1. Therefore, u squared is equal to 2. U squared is equal to 2, implying that u is equal to root 2. Then 2, put it here, 2 cubed is 8, 8 plus 1 is 9. Therefore, u squared is equal to 9, implying that u is equal to 3. So now I can write, when I've changed the variable, to come up with that. So simplifying gives me that. So this and this gives you x cubed, which is here. Then there is this u, and this one, square root of u squared, also it gives you u. Meaning that you can cancel this with this and remain with x cubed. But the good thing, we know that x cubed is equal to u squared minus 1, which is this. And here up, the 2 is maintained. So that is, the denominator can be factorizable. So we factorize it, and the next option is partial fractions. So 2 will be equal to a in brackets u plus 1 plus b in brackets u minus 1. Putting u equal to 1 will give me a as 1. Then putting u equal to negative 1 will give me b as negative 1. Therefore, this integral is the same as this integral. So integrating this gives me that, and integrating this gives me that. Combining the two gives me ln in brackets u minus 1 over u plus 1. Then substituting the upper limit first, I'll come up with ln a half. Then lower limit, I'll come up with that. So ln minus ln is the same as division, so it will be this a half divided by this one. For this division to become a product, you have to get the reciprocal. So that is why you see here here it was root 2 minus 1 over root 2 plus 1, but here it is root 2 plus 1 over root 2 minus 1. Then this denominator is a difference of two squares. That's why you see here 2 minus 1. Then here when you expand, you come up with this, because it will be this squared plus 2ab plus 2 times this, which gives you 2 root 2, then plus this squared, which is 1. So this 2 plus 1 is 3, that is why there is 3 here. But remember that ln is the same as log base e, that is why you see here now log base e, and that is what they wanted. So now we shall go to integration using t formula. So this method is used to integrate quotient functions of sine or cosine. Case 1 is using the variable t equal to tan the given angle. If there is uneven power on sine or cosine of the given quotient, we use t equal to tan the given angle. So as long as you see uneven power, for example, here there is uneven power, t is uneven power, this is also uneven power, there we shall use t equal to tan the given angle. In this case the angle is x, that is why here it is also tan x. Even here there is power here, so it was 4x, even here the angle will be 4x, and so on. In this way the integral will be reduced to a form which is easily integrated. So you'll go through some questions. Question 1 says find this integral. So the power is even, so what we shall do, let t be equal to tan x. Therefore the t dx will be equal to sec squared x, but sec squared x is equal to 1 plus tan squared x, and we already know that t is equal to tan x, therefore we'll come up with 1 plus t squared. Making dx the subject gives you the t over 1 plus t squared. But I have to first simplify this, so simplifying this is this one is the same as this, because I'm going to multiply up and down by 1 over cos squared x. Why do I multiply by 1 over cos squared x? It is because I want to get an expression having tan. And remember, because here it is sine, I have to divide by cos to get tan. That is why I multiply up and down by 1 over cos squared x. So for the numerator, 1 over cos squared x is the same as sec squared x. Then this with this gives you sec squared x, and this with this gives you tan squared x. Then the good thing, I know that sec squared x is equal to 1 plus tan squared x, and which is replaced with that, and this one is also replaced by that. So in the end I'll come up with this one being equal to 1 plus t squared over 1 plus 2t squared. Therefore the given integral is the same as this integral, but you also have to change dx into dt. So we know that dx is equal to this, so where there was dx, we shall put there dt over 1 plus t squared. Then we shall simplify this, and this cancels, you remain with 1 over 1 plus 2t squared dt. So I need this identity to integrate 1 over 1 plus 2t squared. So 1 over 1 plus 2t squared with respect to t, comparing it with this will give you this. But remember, we are the ones who introduced in the t, so we shall come up with, replace the t with tan x. So now we shall go to question 2, which is that find this integral. Now when you look at this integral, the angles are different. This is x and this is 2x. So that means that we have to express this one in terms of x by using the identity that cos 2x is the same as 1 minus 2 sine squared x. So this one is the same as, is replacing this. Then when I collect like terms, I'll come up with 1 over 1 minus 5 sine squared x with respect to x. Therefore now I have this even power, meaning that shall let t be equal to tan x. Differentiate it, I'll come up with dx dt dx being equal to 1 plus t squared, implying that dx is equal to dt over 1 plus t squared. but this one can be we can multiply up and down by 1 over cos squared x. I think you know by now, you know why we multiply by 1 over cos squared x. It is because I want to get an expression in terms of tan. So this gives you sec squared x, and this gives this with this gives you this with this gives you that. So next, so remember that sec squared x is equal to 1 plus tan squared x. So this gives you that, and this gives you this. Then simplifying and expressing in terms of tan will give you this. Therefore, you shall come and say that this integral is the same as this integral, and the dx will be replaced by the t over 1 plus t squared. So this and this cancels, you remain with 1 over 1 minus 4t squared. So this denominator can be factorized to become difference of two squares to come up with this. Therefore, the option is to use partial fractions, which is that, and equating the numerators gives you that line. Then putting x equal to 0.5 gives you that. Putting x equal to negative 0.5 gives you that. Therefore, the partial fraction is this. Now I can go ahead and integrate. So these are the same as this. So integrating this gives you this, and this gives you that. So in the end, that will be the answer. But remember, we are the ones who introduced in the t, so you have to remove the t by putting there tan x. So that was case 1, where t is equal to tan the given angle. But there is a case whereby we have to use t being to mean tan half the given angle. So if there is no power on sine or cosine of the given quotient, we use t equal to tan half the given angle. For example, in this case, there is no power on sine, so we shall use, if this is x, this will be x over 2. And if this is 4x, this will be 2x. So now we shall go to question 1. Question 1, they say that find sec x. Now that sec x the same as 1 over cos x. So in this case, because there is no power, we shall let t be equal to tan x over 2. So when I differentiate, first differentiate the angle to get this a half x, a half, then differentiate tan to come up with x squared. The angle remains as x over 2. But I know that this is the same as this, so in the end I'll come up with a half in brackets 1 plus t squared. Therefore, dx is equal to 2 dt over 1 plus t squared. Now I'll come and substitute. So cos x, I think you remember the t formula for cos x is 1 minus t squared over 1 plus t squared. So reciprocal will be the one for sec x, which is that. But the dx is equal to that, so shall also substitute for dx. Then we shall come here and say that this and this cancel, so remain with this, and this is the difference of two squares, so it can be factorized to give you that. And since it can be factorized, the next option is partial fractions. So equating the numerators gives that. So putting t equal to 1 gives you a as 1, then putting t equal to negative 1 gives you b as 1. Therefore, that integral is the same as this integral and gives you negative ln 1 minus t, and this will give you ln 1 plus t. So when I combine these two, I can come up with this. But remember, we are the ones who are introducing the t, so we shall come and remove that t. So this one is the same as this when I rationalize, and when I open brackets, I'll come up with this. Then when I split, I'll come up with that. Why? Because this one and this one have been paired to give you this. Then this one has been taken to the other part. So in that case, I realize that this one is the same as sec x and this one is the same as tan x, t formula. I think you remember that under trig identities. Therefore, sec this is equal to ln this. Then find integral of cosec x. So cosec is the same as 1 over sine. So because there is no power, we shall let t be equal to tan x over 2. The ratio gives you this. Therefore, dx is equal to that. So integrating this is the same as integrating 1 over sine and the reciprocal and the t formula for sine, and reciprocal of the t formula for sine is 1 plus t squared over 2t, and dx is that. Therefore, simplifying this and this cancels, and this 2 also cancels, so you remain with 1 over t, and integrating 1 over t gives you ln t. But remember, you are the ones introducing the t, so you come and substitute for t as to get ln tan x over 2 plus x. So now we shall go to question 3, which says that find this integral. So let t be equal to tan x over 2. I think you already know that. Therefore, dx will be that. Now we have to simplify this one first in terms of t. So sine x is equal to, is given by that. This one is here, and this one is there. So when I get the LCM for this, I'll come up with this part. Simplifying, collecting like terms, so this and this cancels, you remain with only 2. Well, that's why you see 2 here. Then when this division changes into multiplication, you get the reciprocal for this. So in the end, this and this cancels, and this 2 also cancels, so you remain with only t. So the whole of this is equal to t. Therefore, you come and say that integrating this is the same as this. So, and integrating this will give you this ln in brackets 1 plus t squared. I think you remember that method under further integration. But remember, you're the ones who are introducing the t, so this one will be replaced by tan squared x over 2. So that was question. Now we shall go to question 4, where they want you to find this integral. So let t be equal to tan x over 4. Now x over 4, because here the angle is x over 2, and half of x over 2 is x over 4. So it will, when I differentiate, I'll come up with this, implying that dx is that. So expressing this in terms of t, I'll come up with this. So dx is this, and this one is that. So get LCM for the denominator, I'll come up with this. So simplifying gives you that. So because this and this cancels, so numerator will remain with only 4. You remain with 4, and here you remain with, if I multiply, this is 3 plus 8, and also this is 3t squared minus 5t squared, which will give you negative 2t. Now here it would have been 8 minus 2t squared, and here it would have been 4. So what I did, I reduced both numerator and denominator by 2 by dividing both numerator and denominator by 2. So that's why you see you have 2 instead of 4, and you see 4 instead of 8, and you see t squared instead of 2t squared. Then this one can be factorized, implying that now the next option is partial fractions. So it will be that, then equating the numerators gives that. So putting t equal to 2 gives you that as the value of a. Putting t equal to negative 2 gives you that as the value of b. Therefore, this integral is the same as this integral. Integrating this gives you negative this, and this gives you positive that. So I can choose to substitute for t here, because remember, we are not given t, so we can either substitute here or here. But when I want to begin with a positive, I can do this. so that I can now go ahead and substitute for t. Therefore I'll come up with this integral being equal to this, where there is t, you put there tan x over 4. So now shall go to question 5. Question 5, they want this integral. So we shall let t be equal to tan half the angle. The angle was 2t, so here to be, sorry, the angle was 2x, here the angle will be x. Differentiating it gives you this. That means that dx is equal to that. Therefore this one, t formula for this, for tan x, remember t is tan x, therefore tan x you just push t, and but cos 2x is this 1 minus t squared over 1 plus t squared. I think remember that under trigonometrical identities. So we are not yet covered. If you have not yet gone through the video for trigonometry, I encourage you to first go through it so that you can easily understand this topic. So where there is dx, we shall put there this, that's why you see it here. Then simplifying gives you this, because this one and this one cancels. Then you remain with t over 1 minus t squared dt, which is this. Then integrating this gives you negative a half in brackets 1 minus t squared. But remember, we are not the ones who introduced in the, we are the ones who introduced in the t, so we have substituted it to become that. So now shall go to question 6, which is that find this integral. So shall let t be equal to tan x over 2, therefore dx will be 2 dt over 1 plus x squared. Expressing this in terms of t gives you that, so simplifying gives you 1 minus t squared over 2t squared. So that means that the whole of this is equal to this, so that is why you put it here. Then this dx is here, so that is why you put it here. Simplifying, you'll come up with this. So now the denominator can be factorized, so we shall use partial fractions, and equating the numerators gives you that. So comparing coefficients of t to power 0, here there is 1 here, that's why you see 1 here. Then here there is no t to power 0. Here there is this t to power 0, because 1 times b gives you b, so that's why you see it here. Here there is none. Then for t to power 1, here it is 0, because there is nothing like t, that's why you see this 0. Here there is this times this to give you that. Here there is none, here there is none. Then t squared now there is this with this, sorry, that one doesn't work. There is this with this, that is why you see this b there. Then there is also this with this, that is why you see d here. Then this side there is negative this, which that's why you see negative 1 there. So in the end d will be equal to negative 2. Then t cubed, there is this with this, that is why you see a here. Then there is also this with this, that is why you see c here. This side there is none, that is why you see 0. Therefore c is equal to 0. So that will be our partial fraction. Now we can integrate it. So integrating this gives you negative 1 over t. Integrating this gives you arctan t. Substitute for t, you'll come up with that. So now shall go to question 7, which says that prove that the integral of cosec x over 2 for x between pi and 4 pi over 3 is ln 3. So first of all, the angle, there's no power, so t will be equal to tan half the given angle. Therefore it was, the angle was x over 2, here to be half of it will be x over 4. Then when I differentiate, I'll come up with dx being equal to 4 dt over 1 plus t squared. I also have to change the limits. So the limits for x were pi and 4 pi over 3. So you put there pi and 4 pi over 3. Then the limits of, we are changing it in terms of t. So that means that when I put pi here, I'll come up with tan pi over 4, which is 1. Then when I put pi x, this 4 pi over 3 here, I'll come up with tan pi over 3, which is root 3. Therefore, this integral is the same as this integral. And when I simplify, this and this cancels, then this 2 and this 2 remain with 2. That's why I see 2 here. And here you only remain with this t, that's why you see 1 over t there. Then integrate 1 over t gives you ln t, which is there. The next is to substitute the limits. So substitute, begin with the upper limit, followed by the lower limit. So in the end, but ln 1 is equal to 0, so we'll only remain with 2 ln root 3. And this root 3 is the same as 3 to power a half. Therefore, when that half goes this side, it will become, that is why you see here this a half here, and now there is only 3 here. So this one cancels, you remain with only ln 3, which was required. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on differential equations. So if you haven't yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video on differential equations has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we can all benefit as a family.